Okay, for the example 1, the question is find the maximum flow from S to T. From S to T. Okay, now we need to find the possible path. First, the possible path is S A T, which is S A T. And then we need to find the smallest one of number, which is the 4. So we need to minus for this path. 4 minus 4 is 0, which is 0. And then 8 minus 4 can give us 4. Okay, for the SAT, the maximum flow is 4. Next, the other path that we can calculate is SABT. SABT. And then we need to find the smallest number, which is 4. So 4 minus 4 is 0. 5 minus 4 give us 1. Okay, 1. And then 8 minus 4, it gives us 4. So the maximum for this one is 4. Next, we can go there to T is SCT. Okay, the other path is SCT. Alright, find the smallest one, 7 or 2. So 2 is the smallest one, so we need to minus. 2 minus 2 give us 0, and then 7 minus 2 give us 5. So the maximum is 2 for SCT. Next is SCBT. SCBT. So next, SCBT. Which one is the smallest one? That is 4. So there is 4 and there 4. So we can choose any number to minus because it's same. So 4 minus 4 is 0. And then 4 minus 4 is 0 here too. And then 5 minus 4 is 1. So the maximum here is 4. Okay, next. Okay, so we want to make sure our calculation is correct. So from the source, we get here is 8 and 16. So it's 14. For the sink, we need to calculate 4 plus 8 is 12. And then 8 and plus 2, we got also the 14. So our answer is same, which is 14. Alright. Okay, we continue with exercise 2. This graph show is directed graph because it has arrow. Okay, the question is find a maximum flow from S to T, from here to here. First of all, we need to find possible path from S to T. So we got S to A to B to T. Okay, next we need to find which one is the smallest. We got 250, so we need to minus all capacity with 250. We got 0. This one we got 200, and this one we will get 50. So okay, next, this is 0, so we cannot use SA anymore, so we proceed to SD A B T. Okay, which one is the smallest? 400, 100, 200, and 50. We take 50. 50 minus 50, we got 0. 200 minus 50, we got 150. This one 50. This one we got 350. So here is 50. Okay, next. This one we cannot use anymore because the value is 0. So we take S, D, A, B, C, T. S, D, A, B, C, T. Okay, look. Which one is the smallest? Okay, we get 50. So this one automatically 0. This one 100. This one 3 minus 50, 300. Okay, this one 100, and this one 350. So the smallest one is 50. Okay, next we process. This one we cannot go through because 0. So we only have possible part that S, D, C, and T. D, C, T. Okay, which one is the smallest from these three capacities? So we have 250. Minus get 0, minus get 50, and this one we will get 100. So the maximum is 250. Total up this one, we will get 0, 0, 0, 5, we get 600. Okay, look, how to know that we have the correct answer? We draw again. Okay, sorry for the not very smooth line. Okay, 500 minus 0, we get 500. 400 minus 50, we get 350, right? 300, yes. And for here 300 minus 0, we get 300. 400 minus 100, we get 300. Okay, total up this one, we got 100. Total up this one, we got 100. So the capacity in and out will be the same. Okay, that's all from us. Thank you.
Okay, for example 3, from the node S to node A, the capacity is 6 million gallon of per day. From node A to node B, the capacity is 2 million gallon per day, and so on. In the first step, let's find a path from the S to T. There are several paths. We need to identify one path at this time. For example, this path SABT. Now, in step 2, we need to find the smaller capacity of the arcs on this path. So, 2 is the smaller. Minus 2 from the capacity of each arc on the path. This will be changed to 4. This will be changed to 0, and we can remove it from the network. And this will be changed to 1. Now we add a backward arc from each arc on the path. Add 2 to the capacity of its reverse arc. This will be 2, this will be 2, and this will be 2. So this is a residual flow network. Let's go back to step 1 and check if there is still a path from S to T. There is a path S, C, D, T. We need to find the smallest capacity of the arcs, and this path denoted by 5 minus 5 from the capacity of each arc on the path. This will be 0 and we can remove it from the network. This will be changed to 2 and this will change to 3. Now we add a backward arc from each arc on the path. Add 5 to the capacity of each reverse arc. This will be 5, this will be 5, and this will be 5. So this is a residual flow network. Let's go back to step 1 and check if there is still a path from S to T. Yes, there is path SADT. We need to find the smaller capacity of the arcs on this path, denoted by 3. Minus 3 from the capacity of each arc on the path. This will change to 1, this will be changed to 1, and this will be changed 0, and we can remove it from the network. Now we add a backward arc from each arc on the path. Add 3 to the capacity of each reverse arc. There is already a reverse arc from A to S and its all capacity is 2. So 2 plus 3 equal to 5. There is no reverse arc between D and A, so we need to reverse arc and the capacity is B. The capacity is 3. There is already reverse arc from T to D and its all capacity is 5. So 5 plus 3 equal to 8. So this is a residual flow network. Let's go back to step 1 and check if there is still a path from S to T. We can no longer find a path from S to T, so the optimal solution is determined by the backward arcs. Let's remove the original forward arcs and only keep the backward arcs. This is an optimal solution. That means we should pump 5 gallons of water from S to A, 2 million gallons from A to B, and so on. The maximum flow is 5 plus 5.
Okay, next we proceed to minimum cost flow model. The model for any minimum cost flow problem is represented by a network with a flow passing through it. S1, S2, transshipment, D1 and D2 are called the nodes. S1 and S2 are called a supply node, which is a fixed positive number. Next, D1 and D2 in the Rex triangle is the fixed negative number, which is the demand node. Any node where the net amount of flow generated is fixed at a 0 is a transshipment node. Having the amount of flow out of the node equal to the amount flow into the node is referred to as conservation of flow. The error in the network are called the arc. From this figure, we can see that in a yellow error is the arc.
Okay, folks, welcome back to BFI 12. Now, we just talked about the network optimization, what it is, and what are the different kinds of problems that we face in network optimization, and how it affects your personal day-to-day life, as well as the some of the areas where it is applied in the industry. So what I would like to do is I would like to now next take the minimum cost flow problem. Okay, so here we are looking at the flow of materials or people from one place to the other place, and we want to do that in a minimum cost way. So that's why min cost flow problems. Okay, now here I draw your attention to one of the problems, that is the problem 6.3 in your problem data set. Now the scenario here is there is a factory that uses these boom boxes that these three vendors produce, and the factory has two warehouses. As and when it needs the boxes, it withdraws from its warehouses and uses in the final assembly. Okay, so the cost is each vendor, for a set of 1,000 boom boxes, they charge $22,500. Vendor 1, vendor 2 is $22,700, vendor 3 is $22,300. But unfortunately, so these vendors are located in different parts of the U.S. and likewise, so their distances are different from the warehouses where the factory has. For example, vendor 1 is about 1,600 miles away from warehouse 1 and 400 miles away from warehouse 2, and likewise we have the detail for the other two vendors. Now anytime that we basically bring the consignment from any of these vendors, the shipping company, the trucking company charges $300 flat fee, then 40 cents per mile, okay, as the variable cost of transportation. And so we have these different rates for different vendors from perhaps different trucking companies. And so the total cost of shipment then would be, just the cost of shipment would then be $300, that's a flat fee, plus 40 cents per mile times 1,600 from vendor 1 to warehouse 1. Then for warehouse 2 it would be 300 plus 40 times 400 to warehouse 2. So that is the cost information that we need to get. Okay, but what we want to minimize is the total cost of procurement, not just only the shipment, but the total cost of procurement. That includes the purchase price as well as the shipping cost. So that's the total cost is what we want. Okay, now from each time that a factory needs, it draws it's from its inventory that's in warehouse 1 and warehouse 2. Okay, so that shipping cost is $200 per shipment. Okay, from warehouse 1 to factory 1, and likewise $700 from warehouse 1 to factory 2. So this is a distribution network schematic representation. Each vendor can supply about 10,000 boom boxes. Since we are working in terms of the thousands of units, I will just use 10, 10, 10. So the total supply in these three places is, from all these three places, is 30,000 or 30 units of boom boxes. Factory 1 needs 10 and the factory 2 needs 6 on a monthly basis. So that means we need only 16, but we have a total capacity of 30. So this is an unbalanced problem where the supply exceeds the demand. Okay, now the distribution network basically says vendor 1 can supply to both warehouses, likewise vendor 2 and vendor 3, and both warehouses can supply to both of these factories. So this is the distribution network. On top of that, the problem also states that there is a shipping capacity on each route. So that means vendor 1 can send at most 6 units from V1 to W1, at most 6 units from V1 to W2. If it ends up sending all 10, so it is going to be a combination on this route that will sum up to 10. Okay, but nonetheless on each route he cannot or she cannot supply more than 6. So we have the shipping limitations as 6 on each one of those routes as the problem states. Okay, the next one is to go and then capture these flows. So from, okay, we have the arcs going from to, okay, so from to. So let's just call V1, V2, V3 as 3 vendors, W1, W2 as warehouses, F1 and F2 as the factories. V1 to W1, V1 to W2, V2 W1, V2 W2, and likewise, I have this over here. Okay, now here is the how many units to ship, so that's going to be our decision variable. We don't know. The total cost, as I said, is going to be a combination of the purchase plus the total variable cost. Okay, now here is where I have the variable cost. For example, from vendor 1 to W1, if you look at it, it's going to be $300 flat plus 40 times the distance, and that information is what I have here, 300 plus 40 cents times, that is 0.4 times the distance, and we get that one. So here I have the miles, again taken from the earlier table that I just pointed to. So the next is to get the variable cost of transportation from V1 to W1, V1 to W2 is there, V2 W1, V2 W2, and then V3 W1, V3 W2 based on the flat as well as the cost there. Okay, then the fixed cost here is, this is the cost of procurement. Now, this is the cost of procurement this is the cost of procurement, that we have. Vendor 1 for 1 unit or 10,000 boom boxes is 22,500. That's what we have here. The total cost then is the sum of the cost of procurement and the sum of the transportation. Actually, this should be the transportation cost, this should be the procurement cost. So let me just go and then change this as the transportation cost. Of the shipping cost, and this as the procurement cost of the purchase cost. Okay, purchase cost, and the total cost is sum of the purchase plus the transportation cost, that is that there. So we need to get that for each one of them, and so I'm going to post this on the website for you to get each one of those formulas, but that's how we get it. And so that's the next step to do, is to get the transportation cost. And of course we had to list down what is the shipping capacity on each one of those routes. That is 6 units each, so that's a column that we have here. Okay, now the next one is to get the flows. Okay, so whatever that flows out is going out, let's go with a positive sign. Okay, well, let's go with a positive. Whatever that comes in as a negative sign. Okay, as a negative sign. Okay, now in this problem we have a total supply of 30 units, total demand of 16, so that means we got 14 extra. Now as a management decision, if you want to get this 30 but use only 16 and hold back those 14 as a combination at these places, we don't know what is the best way, the problem would tell us, then in that case, so we can put that as the supply or demand over here. Now I did assume that since the problem does not say that we are going to hold back units at W1 and W2, and it did not say how many, what is the maximum capacity, I just chose it that whatever that comes in should go out. Okay, from each one of these warehouses, whatever that comes in should go out. In that case, the net flow out of warehouse 1 should be 0, and out of warehouse 2 should be 0, because this is what comes in and should go out. Okay, now what is the maximum that V1 can send is up to 10 units. Okay, that's why we have this less than or equal to 10 units, whereas when you take this factory 1, it has only material coming in, so as per our notation that is negative, so that's a negative 10. Okay, and that is an equality, meaning that since if you put that as less than or equal to, the problem will give you 0, because you want to minimize the cost, so the best is not to send any units at all. So it should be equal to or greater than, you can if you want to. So this is going to be 10 units, that's going to be 6 units, but with an equality sign. So here we have a mixed over here. Okay, now so what we want is whatever the thing that flows in, that flows out. Okay, that means V1 W1, then V1 W2 should be that, and from then you go down here, W1 to F1, W1 to F2, W2 to F1, W2 to F2. So the net flow then is going to be, that's how we basically take the net flow. Okay, now what I would like to do is I would like to define the range names. Now for example, which I already have done, so what you could do is, like for example, to define the range names, what you could do, there are two ways. One, you can just block this, then go here and type the name, what you want to call that range name. Or there is another way, is to go and then select the entire thing, then go through the dialog box. I would like you to refer to the naming of the ranges in the tutorial that I have sent, or you can take any book on Microsoft Excel and learn from there how to name these ranges. Okay, range naming is a convenient way over here. So the best way, the most simplest way, is to go highlight the range and type the name. Okay, so like here I would highlight all this range, go and then type in this box from. Okay, likewise there is another range name that I have given, and this is 2. Okay, 2. And the another range name is the decision variable, which is the ship. Okay, and then if you look at here, you basically see all these range names from, to, ship, and the other one is the total cost, is the other one range name that I have. And so if you click onto that one, that tells you this is the total cost. Okay, the total cost is that one. Now once we have that one, now we want to get the relationship. Those relationship is the amount of material that is sent out of vendors should be less than or equal to that, and the amount that comes into W1 and W2 should also go out. So that's that W1 W2 net flow, and whatever that comes into F1 and F2 should be equal to its demand. So that's what we have. So this is how we capture the model relationships. And of course the total cost over here is a sum product of how many units you ship from V1 to W1 times the total cost on that particular route. Okay, so that is the total cost of shipping. What we want to do is we want to minimize the total cost in such a way that these relationships are maintained. Now we have to get the relationship now here in terms of the net flow. Now if you do this, this is the command that I have, is sum if, okay, from J33 ship minus that. Okay, and this is a common command or the formula that we use. Then we just copy them down. What does it say? Sum if, meaning that go from this list, from the list that we have here. J33 is what is here in J33 V1. In other words, go to the list from and only take the V1 from the list, only V1 from the list, and go and then sum those, basically how much gets written here from V1. So those are the two places in that case it is going to be. Okay, and that is ship. Likewise, since we are talking about the net flow, this is going out and this is coming in. Of course nothing is coming in, V1, V2, V3. Okay, so this is going to be 0 there. But if you look at W2, think that W2 would be whatever that comes into W1, W2. Let me go down to that and discuss with respect to that. Okay, now here, sum if from. Okay, go to the from list and then take J36. J36 is W1. Go and then take only those W1s. Okay, these are the two places. Sum what basically goes out in these two cells here, that is a ship. Okay, look into that one. This is going out. Now minus what is coming in. Sum if. Now come to the to list, that is W1 here, W1 here, W1 here. So take that from the to list and W1, 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 look at the corresponding ship cells, add them up. So this is what comes in should go out. What comes in minus what goes out. Okay, so that is that command. Okay, so once you have that relationships, then just copy the command down. Copy the command down to all the cells. Now go highlight that. Go to the solver, data solver. Now solve. What we want to do is we want to minimize the total cost. Minimize that. Subject changing cells are my shipping. How much that I want to ship. You can highlight the range or you can just type the ship. Okay. Add the constraints. The constraints are, okay, the amount that you ship on each one of these route first has to be less than or equal to the capacity on that route. Okay, so that is the shipping capacity and that route. Okay, so that's one set of constraints. The amount that is shipped has to be less than or equal to the amount, the capacity, and that route. Then add the constraint. That constraint is this net flow. The first three are less than or equal to, so block these three. That should be less than or equal to the amount that goes out of the vendor should be equal to or less than their capacity. Add. Then now the next set are equality constraints. So let's just go block all of them into one, equal to that. Okay, now we got the relationship. The amount that we ship has to be less than or equal to the capacity on those routes, and the supply and demands of these vendors, warehouses, and factories need to be satisfied. Click OK. Options, linear, non-negative. Click OK and solve. Okay. When you solve found a solution. All conditions are satisfied. Click OK. Now what does this recommendation say? The total cost of shipping is $374,460. So vendor 1 is not going to supply any shipments to warehouse 1, but will send 6. So that means out of 10, vendor 1 is going to supply only 6. Vendor 2 is going to supply 6 to warehouse 1 and nothing to warehouse 2. All 6 will go to warehouse 1. Vendor 3 is going to supply 4 units to warehouse 2. In other words, warehouse 1 will receive 6 units and warehouse 2 will receive 10 units. So 6 and 10, that is 16. And warehouse 1 will send all the 6 units to factory 1, whereas warehouse 2 would send 4 units to factory 1 and 6 units to factory 2. So this is the minimum cost. And then if you were to change from this shipping route any other assignment, the cost is going to go up. The cost is going to go up. And this is the minimal cost. Okay, this is the minimal cost. And you can run a sensitivity analysis report on that one to see, which vendor is more cost effective, meaning that, let me kind of do that too. Let me go back to this problem. Solver. Solve. So if you go back to that cell, then do the solver, solve, and then click on sensitivity and click OK, you get the sensitivity report. And what the sensitivity report basically says here is, if you look at it, the first 3 cells, the first 2 are V1 to vendor 1 and 2, over warehouse 1 and 2. This is V2, this is V3.
Programming formulation of the transportation problem. In a transportation problem, the goal is to produce products at supply locations or origins and transport them to destinations where they are demanded at minimum costs. We will be writing an LP formulation for this transportation matrix. The origins are 2 plants at Boston and Toronto with supplies or capacities of 300 and 500 units, while the destinations are 3 distribution centers with demands of 200, 300, and 250 respectively. The costs of transporting a unit of the product from origins to destinations are seen here. For example, it costs $6 to ship a unit of the product from Boston to distribution center 2. Now let's draw a transportation network for this problem. These circles are called nodes for the origins, or in this case, plants. And these are the nodes for the destinations. Here are the plant capacities and here are the demands at the destinations. Here are the shipping costs from Boston to the distribution centers, and here are the costs from Toronto. The arrows from the origins to destinations are called arcs. Now let's define the decision variables for this LP model. Let XB1 equal the number of units shipped from Boston to DC1, then XB2 from Boston to DC2, and XB3 to DC3. Similarly for Toronto, we can use XT1, XT2, and XT3. The number of decision variables is simply the number of origins multiplied by the number of destinations. In this case, 2 times 3, which equals 6 decision variables. Now, suppose I don't like listing every single variable, or maybe I just happen to have too many variables. Then I can use the short form as follows. Let Xij equal the number of units shipped from plant I to DCJ, where I equals B for Boston and T for Toronto, and J equals 1, 2, 3 for DC1, DC2, and DC3 respectively. Next, we can state the objective function. Since the objective function is to minimize cost, we write the objective function as follows. Minimize 5 times the number of units shipped from Boston to DC1 plus 6 times the number of units shipped to DC2 and so on. Note that every single cost is accounted for in the objective function. For the constraints, we need to write 1 for every node. For Boston supply, the total amount shipped to the 3 destination centers cannot exceed Boston's capacity, which is 300. So we write XB1 plus XB2 plus XB3 is less or equal to 300. We do the same for Toronto. XT1 plus XT2 plus XT3 is less than or equal to 500. Note here that total supply exceeds total demand. That is, we will not end up exhausting capacity. And that's why we use the less than or equal sign. For DC1 node, we write XB1 plus XT1 equals 200. Equality is used because we have a demand here that must be met, and we have enough supply to meet it. Similarly, for DC2, we have XB2 plus XT2 equals 300, and for DC3, we have XB3 plus XT3 equals 250. For non-negativity, we can either list all the variables and state that each is greater than or equal to 0, or we can simply write Xij is greater or equal to 0 for all I and j. And that's the LP model. Furthermore, let's suppose the cost of producing a unit of the product is $20 in Boston and $18 in Toronto. Then we simply add 20 to the shipping cost per unit of the product from Boston and add 18 to those from Toronto. The objective function is thus updated accordingly. Note here that if total supply were to equal total demand, we could have used equality for all constraints. We refer to that situation as a balanced transportation problem. This problem, however, is an unbalanced transportation example where supply exceeds demand. Moreover, we could also have an unbalanced problem where demand exceeds supply. Consider the following scenario. Suppose demand at distribution center 1 increases to 300 units. Then we have another unbalanced problem with demand exceeding supply. Let's look at 2 ways to handle this. Since demand now exceeds supply by 50 units, one approach is to add a dummy plant and assign it a supply of 50 units. Note that these 50 units do not exist, so their cost per unit is 0 and their shipping cost is also 0 since they're not going to be shipped at all. We can thus modify our model as follows. Add D for dummy in the decision variables. Add the new cost to the objective function. They won't really have an impact on total cost. Next, we add a constraint for the dummy node, and then add the units assumed to be shipped from the dummy to the distribution centers. And again, Xij is non-negative for all I and j. At the end of the day, demand will not be fully satisfied at some of the distribution centers because the dummy supplies don't really exist. Instead of introducing a dummy, let's now look at another formulation method we could apply. Since demand exceeds supply, all available supply will be used up. So we simply change the less than or equal signs here to equal signs. And since demand is not going to be fully met at some of the distribution centers, we change the demand equality signs to less than or equal signs. And the model is again complete. Now, suppose for some reason we're not allowed to ship from Toronto to Distribution Center 3, maybe because the cost is too high or the destination is too far. One way to address that is to simply remove XT3 from the model. But if your model has too many variables and you don't want to be looking for XT3 all over the place, a better way is to add another constraint to the model that states that XT3 equals 0. And that addresses the issue. And that's LP for transportation problem. Thanks for watching.
Okay, so in this video, we're going to solve a minimum cost flow problem. So we're given this directed graph. it looks like we need vertices A and B to send 10 units of flow. We need vertex D to receive 20 units of flow, and we want to do this minimizing the total cost, and the costs are given by these red numbers here. And we're also given that the capacity for edge BD is 5, and the capacity for the rest of the edges is infinity. Okay, so we're going to do this using the network simplex method. We're given that this initial basic spanning tree is going to be BA, AC, CD. So let's sort of calculate what is our initial basic feasible solution. And it's easy to do that since this is a tree. Well, our solution is going to look like this, and B needs to send 10 units of flow total, so this arc has to receive 10 units of flow. A needs to send 10 units of flow total, so it's receiving 10 already, so this arc needs to have 20 units of flow going through it. And C is a transshipment node, so it's getting 20 units of flow. It needs to send 20 more units of flow out. So this is our initial basic feasible solution, and let's see if it's optimal. So how could it not be optimal? Well, one of the non-basic variables maybe could be increased, and our cost could decrease. So what are our two options? We need to see what happens if we increase the flow going through arc BD, and we need to see what happens if we increase the flow going through arc DA. So let's make this table here where we decide if our solution is optimal or not. So there are two arcs that we need to consider, arc BD and arc DA. And since this is a spanning tree, each of these arcs, if I add flow through one of these arcs, this is a spanning tree, so it's going to create a cycle in our graph down here. And so in this case, if I add the arc BD, it will create this 4 cycle here. So it'll create this cycle B to D to C to A. And if I add the arc DA, it'll create this triangle here, D to A to C. And we want to know, okay, what happens if I do indeed add flow along, say, edge BD, what is going to happen to my cost? So let's look at what is the change in the cost per unit of flow. So if I add flow going through BD here, if I add 1 unit of flow going through BD, then I'm increasing my cost by 2, because that's how much it costs to send a unit of flow through BD. So I'm going to increase my cost by 2 by sending this unit. But now D needs to receive 20 units total. So if it's receiving 1 unit from here, then this means that I'm decreasing the flow 1 unit from here, so that in total the flow into D remains the same. So if I decrease flow through this arc, then my cost is actually going to decrease by 5. So this is minus 5. And if flow through this arc decreases, then flow through this arc has to decrease because C is a transshipment node. So I'm decreasing the flow through this, so my cost goes down by 3. And same thing for this arc, I'm going to decrease flow through this arc by a unit, so my cost is going to go down by 1. So here what we're saying is that if I increase flow through this arc BD, my net cost is actually going to be decreased by 7 units. So this is strictly less than 0. Again, we can see what happens if we increase flow through DA. So if we increase flow through DA, then flow through AC is going to have to increase as well, because extra flow is going into A, so extra flow needs to come out of it. And then same thing, flow is going to have to increase through CD. So if I increase flow through DA, if I add 1 unit, this costs 4. If I add 1 unit of flow through AC, this costs 3. If I add 1 unit of flow through CD, this costs 5. So adding a unit of flow through this arc DA is actually increasing the flow through all of these arcs. It's increasing my total cost through all of them. So this is going to be 12, which is greater than 0. So we want to minimize our cost. So we do want to increase flow through BD, and we do not want to increase flow through DA. So BD is going to be our entering basic variable here, our entering basic arc. So this is our entering basic arc. I'll draw it in blue here. And we want to increase this until we find our leaving basic variable, right? So I'll say that we're going to send theta units through here. And what's happening is theta units are going through here, and we decided when we did this calculation that this means each of these three arcs are decreasing by theta units. So none of these arcs can go below 0, so this means that theta is less than 20 for this one, theta is less than 20 for this one, theta is less than 10 for this one. But how much can it increase? The capacity of this arc BD is 5, so actually theta is less than or equal to 5. So this one is the most strict condition, so this one is actually going to be our leaving basic variable. So we're in this kind of interesting situation where the arc BD was the entering basic variable, but it's the first one to reach its upper bound, so it's also the leaving basic variable. This is okay, so this is fine, but what's happening is we are increasing this theta up to 5, so we're increasing the flow of arc BD up to 5, and this is reaching the upper bound here. So we have to update our table and use this upper bound technique and sort of imagine that we're sending 5 units of flow this way, and then re-update this graph. So let's draw our new graph where we imagine that we're sending 5 units of flow this way and make a new decision variable that tells me how many units of flow am I taking back. So let's update our graph. A, B, C, D. And now the net flow is gonna be different from here because we're imagining that we're already sending 5 units of flow from B to D. So B is already sending 5 units. It needs to send 10 total. So now in this new graph, the net flow from B needs to be 5. Nothing is changing about A, and nothing is changing about C. But D needed to receive 20 units. It's already receiving 5, so now it only needs to receive 15 more units. And now all of the rest of the arcs are going to be the same, except for this one that we are reversing. And now this new arc is going to represent how many units of flow are going back here. And all of the costs are going to be the same, except this one's now negative, because this how many units of flow we're canceling out is reducing my cost, right? So this is cost 1, cost 4, cost 3, cost 5, and now this one is cost negative 2. And so the capacity of this arc UDB, the most that we can cancel out is still 5. And the rest of the capacities are infinity. And so now let's see what's happening. Our basic feasible solution now is it's still almost the same. I mean, it's the same set of arcs, but these have been updated, right? I sent 5 units this way. I had to decrease these by 5. So our basic feasible solution looks like this. A, B, C, D. Now I'm sending only 5 units from B to A, only 15 units from A to C, and only 15 units from C to D. And this is our basic feasible solution in this updated graph. So here, like I've imagined that I've already sent 5 units this way. So this is the basic feasible solution. And now we can do the same thing. We can check, is this solution optimal? So what do I need to check? I need to check if adding flow through this arc D to A is going to decrease my cost, or if adding flow through this new arc D to B, or you can think of it as reducing flow in the previous example, is gonna decrease my cost. So let's make this table again, where I check if I add arc D to B, what's happening, or if I add flow through arc D to A, what's happening, because these are the only 2 arcs that I could possibly add flow through. And so if I add flow through arc DB, it creates this cycle DBAC. And if I add flow through arc DA, it creates this cycle DAC. And I can ask, what is going to be the change in my objective function if I do that? What is going to be the change in my cost? And now if I look at the second line, you'll notice that nothing has changed about this cycle here. So this calculation is going to be exactly the same. Adding flow through edge D to A is going to increase my cost. It's exactly the same calculation as before. And if you think about it for a second, I mean, we can do the calculation here. What's going to happen is if I add flow from D to B, well then this is going to actually decrease my cost because the cost here is negative, right? But if I add flow from D to B, then I'm going to have to add flow from B to A because I need to keep the net flow at B the same. So I'm going to have to increase the flow from B to A, so this is going to incur a cost of 1. Same thing, I'm going to have to increase flow from A to C, so this is going to incur a cost of 3. And I'm going to have to increase flow from C to D, so this is going to incur a cost of 5. So this net cost is going to be positive as well. And we maybe could have done that without doing the calculation, because what's happening is I'm just reversing flow from before. We calculated that if I increase flow this way, it was helping me. So if I reverse this flow, it's gonna hurt me. So here we've checked for optimality, and we are optimal. Increasing any of the non-basic variables is going to increase our costs, which we're trying to minimize. So here we're at an optimal solution. So the optimal solution is send 15 units from A to C, send 15 units from C to D, send 5 units from B to A, and we're almost done, except we have to remember that this, we're not in our original graph, right? We're in kind of this updated graph where we've already imagined that we're sending 5 units this way, so we need to remember that we're sending 5 units from B to D here. And this is our optimal solution, and this is the minimum. This will give the minimum cost.